Hello, my name is Elder Giffin, and I would like to share with you the most amazing workbook. And today, I'm going to be looking at yet another Excel workbook tool. This time, hopefully this will be the final one. No promises, but this is re.DESIGN. So again, I've uploaded it into the Dropbox, you can find it there, but I'll be using it from my local desktop here, re.DESIGN. So what is re.DESIGN? Very similar to restruct, except now re.DESIGN is intended to be a fully functional topology optimization tool. And if you're not familiar with topology optimization, you can do a quick Google search and you'll get all these really nifty pictures of what topology optimization is. And basically, topology optimization is just a method of evaluating the topology or the interconnectedness of the material of a structure in order to figure out what the optimal configuration is for that structure. So you can see basically an initial guess at what a topology should be. You know, in this picture, basically you can see you have this standard block, and then you push down on the middle, and then basically using topology optimization, you can determine where you should place the material in that structure, and in order to obtain an optimally performing and optimally structurally efficient structure. So that's pretty much topology optimization in a nutshell. And basically how the program works is very similar to how restruct works. Basically you can kind of open up your file, and I'm just going to be using my Hemi topology SBD, and basically this file in particular is just nothing more than I have my basic frame section kind of on the bottom here, and it actually has applied to it all of the loads that I would have applied had I made it through basically ProtoBridge. And in fact, that's exactly how I got these loads on this, rather than kind of doing it all by hand. So I just assigned all the loads to these frame sections along the bottom using ProtoBridge, and then I deleted the rest of the structure except for just half of the bridge and just the decking support surface with all my loads applied to it. I put pin and roller supports at the bottom, and then I filled up pretty much the entire top part of the bridge, not with members, not with frame sections, but with area sections or shell elements. So if you remember maybe from the learning exercise we did with treating beams like trusses and so forth, basically I'm using that same principle and just filling it up with area elements or shell elements, and each one of these little pieces here is a shell. So basically what I'm going to do is I'm going to basically run my model, get all the data results from that, and then I'm going to basically increment based on how much stress is in each individual shell element in this grid. I'm going to change the density of this particular cell, for each cell. And if it carries more stress, then I'll increase the density, which means it'll have an increased amount of weight, but it'll also increase its individual stiffness. So basically, as we continue to iterate, it should be the case that basically cells that take more load should get more density, and those that basically take less load should decrease in density. And thus, in the final iterate version, we should be able to determine where the most dense portions of the structure should be. And thus, we can determine more or less what the overall shape or topology of our structure should look like. Alright, so that's enough background. You can define your scoring criteria in a very similar fashion as we did with restruct. Now, the only difference here is that I'm only applying deflection readings on this particular side of the bridge, because we're completely neglecting the other side of the bridge. It's only half of the bridge. So you can see for the regular cases it's only measured on the A side, and for the reverted measurements it's on the B side, or the flipped version. I don't know. This is technically still the A side, even though it says B. Now, basically what you can do is, in a similar fashion, define how many vertical cells you have in your model. In this case, there's 16 cells along the top, and then there's 103 cells along this side. Now, I'm not going to do redesign for cost, but you can select how many iterations you want to do. So you can put in, I don't know, like 3, and then pretty much just leave it for an hour or something, or half an hour more like. Click redesign for cost, and it'll automatically iterate 3 times. I'm not going to do it because it takes a while. Each iteration, like I said, last time is maybe 10 minutes, more time than I'd like to spend in this video. But if you do that a couple times, and I've done it maybe 4 or 5 times for this particular model, I've gotten it down so that now I have my results, and once you have completed this button and it's finished all the iterations, it'll print the results for the density field in your model to the density map here on the density tab. So here's what it looks like. So you can see basically blue is close to no density, and if you click on the cell you can actually see what the value is. That's why all these cells appear to have zeros in them. Technically, technically each of these cells pretty much is filled up with the actual value of what the density is. So here it's pretty low density. It's 10 to the minus 10 basically, but if you get up to the top, you know, it gets a little bit bigger, so 0.01. So a lot more material is being allocated to those locations, and you can kind of see more or less as you iterate over time. Each one of these boxes represents one of those shell elements in our original model, and basically you can see if it's green, that means it's slightly more material than the blue certainly, and red is a lot of material. So wow, so this is more or less what our bridge would look like optimally if we could basically construct it out of shell elements. Now unfortunately we can't construct it out of a bunch of little plates and then weld those plates together. We kind of have to use truss members and frame sections ultimately when we do our final analysis, but this gives us a reasonably good idea of what our structure should look like. Now bear in mind this is actually constructed for the 2014 rules, so don't go thinking this is, oh wow, this is what we should do this year. No. So if you like, I could or instruct you maybe how to basically use redesign in order to get this kind of plot for the rules according to 2015. And that'd be really nice, because then you could basically see, okay, well, if I want my top chords to follow a particular path, but I don't really know what the optimal kind of shape of that over-truss structure would look like, then you can kind of use this as a very good guide to give you an idea of, okay, so I want my first chord to come up maybe here, and then it looks like maybe I have like tendons coming up from the decking like this, diagonally, and so on and so forth. And it gives you a really good idea of where you should place your members when you're just designing in AutoCAD. So hopefully that was pretty cool. Hopefully I didn't talk your ear off. Good luck. I'll see you next time.